Good evening or morning or afternoon, as the case may be. Welcome to my laboratory. You're not going to believe this. This is really cute. Okay, so what I've done is I've replaced the MOSFET with BC337-25 transistor and replaced the base resistor with a 1K and removed the 1 megohm resistor. And so here we have a collector base emitter on that transistor. And now I'm able to switch and drive the motor all the way down to the bottom limit of operation of the Hall effect sensor. Right now I'm running at 2.72 volts. Remember that number, 2.72 volts. And that's actually coming from the power supply there. But I have it in parallel with this 10 farad capacitor arrangement here. That's 10 farad supercap, and then these are two 1 farads in series, so they're not really adding very much. So you could call that a 10.5 farad capacitor stack, and that's in parallel. So that's holding the voltage at 2.72 because we're supplying it with a power supply, but I'll be disconnecting the power supply in a few minutes. At any rate, 2.72, the rotor is turning nicely. This is the base signal here, and this is, let's see, there's where the baseline is right there, and we are at 1 volt per division, and so the base signal is going high, then low, then high, then low, not quite to 1 volt, but the transistor is switching cleanly. Now the frequency, we're at 5 milliseconds per division, so we have 5, 10, 15, 20, 22 milliseconds per cycle, right? So we go 1 divided by 0.022 equals 45.45 hertz times 60 seconds per minute equals 2727. So we're at 27.2 or 27.3, or I'm sorry, 2.73 kilohertz, or 2727 RPM, right? At 2.72 volts, and let's just confirm that with the strobe attack. So there's the freezing of motion, and there's the strobe attack indication. It says 28:15 about, or no, 28:20, 28:30 about, something like that. Alright. So we are in agreement between the oscilloscope and the strobe attack. We're turning right about 2700 or 2800 RPM. 2800 RPM at 2.72 volts. We're going 27 RPM. And now, let me turn off the strobe attack. Now I will disconnect the power supply and we will watch the thing. There's too much glare. Okay, we'll watch it run down. When the green light stops flashing is when the Hall effect sensor stops switching. And it's only supposed to work down to 4 volts, and here obviously we're operating at a much lower voltage. So now it's running strictly on the capacitor supply voltage, and it is running down slowly. Sorry about the glare. What happens if I turn off the overhead light? Oh, that's too dark. That won't work. How about if I get over here? There we go. That's less glare. Okay, so when that little green light goes out, then the Hall sensor will no longer be switching the power through the BC337 transistor to the coils. So 2.54 volts, it's still running. Now the spikes on the capacitor go up to about 3 times whatever the supply voltage is down at these low speeds with this transistor. I may be able to improve that again by using a different transistor. But I'm surprised, as it is, still switching, starting to get down there to where it's going to fail in a moment. .4 volts. Oh, there it goes. It died at 2.36 or 2.37 volts. That's amazing. The Hall sensor continues to switch at a volt and a half below its already low spec of 4 volts. Thank you for watching.